Hello there, Mr. Sutton bringing you this lesson on conditional probability with tree diagrams. In this one, we're going to find conditional probability using these diagrams, and as a real-life application, we will determine the relationship between studying and passing exams. For our warm-up, let's say a bag contains 3 red and 2 blue counters. Counters taken at random from the bag and its colors noted. Then a second counter is drawn without replacing the first one. Make a tree diagram to show the possible outcomes. So if you know how to do one of these already, pause the video and see if you still got it. All right, so let's do our tree diagram here. We're going to start by writing the probability of each individual event, and we're going to make each of these a branch. So our first event is we're either picking a red or a blue counter. There is a 3/5 chance that we pick a red counter and a 2/5 chance that we pick a blue counter. So these are different trees, different paths that we might go down. Let's do the second event now. So the second event is we're picking either a red or a blue counter again. Now, if we've already picked a red counter, then there is a 2 out of 4 possibility that we're picking another one, or a 1/2 probability. If we pick a blue counter, then there's actually a 1/2 possibility that we pick one of those, because there's 2 of those left if you picked a red counter the first time. Next, if we already picked a blue counter, well, then we still have 3 red counters left. There's a 3 out of 4 probability that we're picking a red counter, and there's a 1 out of 4 probability that we have a blue counter. Moving on now, we're now going to write the probability of each compound event at the end. So, for example, if I pick a red counter and then a red counter again, given that I already picked the first red counter, basically multiply these together. So we have 3/5 times 1/2. That's going to be 3/10. Next, we have 3/5 times 1/2, which is still 3/10, hasn't changed in the last 5 seconds. 2/5 times 3/4, that's 6/20, or 3/10. And then finally, 2/5 times 1/4, that's 2/20, which is going to be 1/10. And as a last little check here, the compound probabilities should all add up to 1. All possibilities should be accounted for by the time you get to the end of your tree. So we're going to take this tree diagram a little further in the next problem and actually use it to answer some questions. A different problem, though. This one, we have a university professor who fails 20% of his students in the final, and after the final asks them how many actually studied more than 3 hours for it. Those who passed the final, 72% said they studied, and the failures, 31% of them said they studied. So we want to make a tree diagram for the problem and then answer a few questions on the next few slides. Pause the video and see if you can create a tree diagram kind of like we did for the counters in the warm-up. Alright, so creating this tree diagram, we have 2 choices to make. One is, did a student fail or pass? And the other is, did they study or not study more than 3 hours? So just kind of logically thinking this through, it would kind of make sense to say, well, study versus not study, that seems to be the first decision, and then after that, they either failed or passed. Unfortunately, that's not how this is going to go, because if you're going to start with the decision of studying versus not studying, you need to know what percentage of all students studied and didn't study. But they didn't give us that information. They gave us a percentage of students who passed, who studied, and they gave us a percentage of students who failed, who studied. So we have to start with the question, the choice that they gave us the information about for all the students, and that is whether students passed or failed. They told us 20% failed the final. So our first decision then is pass versus fail. And that means if 20% failed, hey, my glass is half full. 80% passed. So we're going to write pass 0.8. Our other branch then will be fail 0.2. And I'm going to do all of this in terms of decimals now. I'm not going to worry about writing percents or fractions or anything else. All right, so now the next choice is, did they study or not study? So looking at the people who passed, 72% said they studied for the exam. So we can say study 0.72. And that means that out of them, 28% said they didn't study a whole lot. So that's 0.28 for no study. We're going to do the same branch down here now. Of the failures, 31% said they studied, so that would be 0.31 for study, and then 0.69, that's 1 minus 0.31, for no study. Now we're going to need the calculator to get these leaves at the end here. Let me grab that one. So for the first leaf, we've got 0.8 times 0.72, giving us 0.576. And then let me just go grab my input there and do 0.28 times 0.8. So that's 0.224. So here's what we have so far. Now let's do the next two leaves. So I'm going to go back up here and grab this input. We're going to do now 0.2 times 0.31, giving us 0.062. And then we'll grab the input again, and now we're going to do a 6.9 instead of 3.1 there. That gives us 0.138. So there are the last two leaves. And now in the next few pages, we're going to use this information to answer a couple questions about these students. So for part A on this example, we want to find the probability that a student studies. And this is going to be expressed as a decimal. So using the information here, see if you can figure out how to do that. All right, so this is a little bit trickier because we can't just look at one of these individual branches. We actually have to look at the leaves for this one. So if you want to find probability of an event that occurs on multiple branches, like here we have studying, down here we have studying, so multiple branches, you're going to need to add the leaves coming from those branches together. So we need the probability that a student studied, given that they passed, and we also need the probability that a student studied and failed. So we've got 0.576 plus 0.062, whatever that adds up to. Which, doing this on the calculator, just to be on the safe side, 0.638. We're going to try part B now, where we have to find the probability that a student doesn't study. So this is kind of like part A. If you didn't really understand part A the first time around, well, hopefully you understand it better and you can give part B a better shot. All right, let's see how that went. So we need to add up the branches where a student does not study. So we have a no study leaf right here of 0.224, and here's another no study leaf of 0.138. We'll add those together now. And doing that on the calculator, we get 0.362. So that was one way to get this answer. Another way, if you remembered the probability that students did study, you could have just subtracted that 0.638 number from 1 and gotten this probability of 0.362. So different ways to do it. For part C, we're trying to find the probability that if a student studies, he passes. When we're dealing with one of these if A then B kind of statements, we're dealing with conditional probability. Conditional probability, a good formula for this, if you're trying to find the probability of some event given another event, then you need to take the probability that both events happen and divide it by all the times that that first event happened. Because that's all really interested in, right? We're just taking all the times the first event happened, and we're just curious how many of those actually worked out the way we wanted. So in this context, if you're trying to find the probability that a student passed, given that they studied, you need to take the probability that they did both, passed and studied, and divide it by the probability that they studied. So we're basically looking at all the students who studied and only those students, and we're asking, well, what percentage of those students also passed? So for numbers, passed and studied, we're using this branch up here, 0.576, that's the past study branch, and we're dividing that by all the students who studied, which we found out earlier was 0.638. That was when you took this past study branch and added into it this pass-fail branch, these poor people who failed even though they studied a whole lot. So taking a look at that percentage now on the calculator, that's going to give us 0.903 if we round that off, so about 90.3%. So basically, the probability that a student passes if they studied is over 90%. So, you know, if you did study, there's a pretty good chance you passed. Conditional probability can be tricky, so here's 3 more examples for you to practice this out based on what you saw in Part C. Give it a shot. All right, so for Part D, if a student studies, he fails. Now we're looking for failure given studying. So let's look for the study fail kids. That's, let's see. studying and failing, that's this group right here, the 0.062s. And then we're going to divide that again by the probability that you studied. That was that 0.638 that we used on the last problem. Let's go to the calculator. So dividing that out, we get another percentage of 0.097. So about 9.7% of the kids who studied failed anyway. Let's look at the next one now. If a student doesn't study, he fails. So this is failure given no study. So let's look at the probability that both happened. So here's no study and fail. That's this 0.138 branch. And then we're going to divide that by the probability that you didn't study. So that was the 1.38 combined with the 0.224 from the no studying pass group, which again, that added up to 0.362. We found that in an earlier problem. Let's do that on the calculator now. And that's going to give us a percentage of 0.381, so 38.1%. So this is the percentage of students who failed from the group that didn't study. All right, last one. If a student doesn't study, he passes. So this is the one where if you don't like doing work, you're hoping this is pretty high. Let's take a look at what happens now. So this is passing given not studying. So again, we've got an overall group of not studying of 0.362. Now the pass and no study branch, that's this branch right here, that's the 0.224. That's what we're dividing now by 0.362. And I showed where I was getting the numbers from, but it is really just 0.362. There we go. And let's go ahead and do that on the calculator. And that gives us a percentage of 61.9, so 0.619. So that's, I guess if you're a teacher, that's kind of disturbing. Like, of the students who did not study, 61.9% of them still passed. But hey, maybe they paid attention in class. We're going to do one more example, and since we already covered an academic example, we'll do an athletic one now. A particular football team is known to run 30% of its plays to the left and 70% to the right. Linebacker on the opposing team notes that the right guard shifts his stance most of the time, 80% when plays go to the right, and that he uses a balanced stance the rest of the time. When plays go left, he takes a balanced stance 90% of the time and a shift stance the remaining 10%. What a mess all of this is, right? What's the probability that a play will go to the left if the guard is balanced? So this is a perfect one for a tree diagram. Pause the video and see if you can come up with a tree diagram for this and then solve this problem. All right, so if I'm making my tree diagram, again, I've got two decisions. I'm going to do my first decision based on the information they gave me about the whole population here. The whole population is all of the plays. So they told us 30% of the plays go to the left, 70% go to the right. So I'm going to put that in my first branch for my tree. So I'm going to say left is going to be 0.3 and right is going to be 0.7. Now, they said that we're either doing a shift stance or a balance stance. For the left here, they told us that when plays go left, we do a shift stance 10% of the time. So I'm going to write shift 0.1. And we do a balanced stance 0.9 of the time. And if plays are going right, they told us that, let's see, we're going to be doing a shift stance 80% of the time. So I'm going to write shift 0.8. And then we have a balanced stance the rest of the time, so that's 0.2. Now for my leaves, I could probably do this without a calculator. So we're going to have the left and the shift, that's going to be 0.03. Left and balance, that's going to be 0.27. Right and shift, that's going to be 0.56. And then right and balance, that's going to be 0.14. And we can just quickly check. This is 0.3 here, this is 0.7 here, so it all adds up to 1, like it should. Awesome. Now that we've constructed our tree, let's use it to answer the question. What's the probability that a play will go to the left if the guard is balanced? So we're looking for the probability of left given balanced. So we need to do left and balanced. That's going to be 0.27 divided by, now we have to do all of the balances here. So we have left balance of 0.27 plus right balance of 0.14. So this is probability of going left and balanced. This is left balanced. This is right balanced. Let's see what all of that adds up to. Plugging that in, that's going to give us a grand total of 0.659, which is basically saying that there's a 65.9% chance that if the guard is balanced, we're going to the left. So that's it for tree diagrams. Hopefully this lesson was a touchdown for you. Till next time, Mr. Sutton signing off. Hut, hut, hike!